Welcome back to another day of 30 days of machine learning. Today we are at day 12 out of 30 from 30 days. It's been 11 days of a lot of fun, a lot of variety in the models that we have built. Let's see what do we have on day 12. So we have a dimensionality reduction using PCA. Now to be honest, this isn't really a model, but it's really like a cool experiment to do, like a very good mathematical trick that we can implement before building the model. So we will deep dive into this, into the entirety of dimensionality reduction. Why do we do whatever we do in this? Okay. So, basically the agenda for today, it's pretty simple. So what I have done is that, we are implementing dimensionality reduction on a real-time data set. So we have got the breast cancer classification problem right here. So we have built this model, this breast cancer classification model before as well. But the model building here is not really the point. Our primary agenda here is to study the effect of, PCA using which is basically reducing the dimensionality of the data set. So what we'll do is we'll do it like an experiment. We'll first build the model like we do usually, and then after that, in the next step, we'll first apply the PCA, reduce the dimensionality, and then build the model again. And in the end, we basically compare the results end to end. And we are also including the entire working of PCA from scratch. So believe me when I say this, this will be one of the best explanations of PCA that you'll get on the internet. And the reason for that is because I will try to do everything from scratch. There will be no black boxes in this video. Anything you have as a doubt, or as a, like, you think it is a black box that you don't really know the answer to, I will try and cover it in here. Okay, so let's begin. Let me open the board quickly. Okay, so very quickly, see, we have got nothing but a dimensionality reduction problem on our hands. Okay, so let me just write it if I can. Okay, so when I write dimensionality reduction, what do you see first? You see the word dimension, right? So what is this dimension that we are talking about, and why are we so eager to discuss it? This is the first primary part of this video, understanding what a dimension even is. Why are we using it? What it is, simple as that. If we are trying to reduce something, we should at least have a good idea as to what it is and what it is actually representing. So let's discuss about that. So dimension, you can understand it pretty simply. So let's say that you have got a data set on our hands, like we have on our hands. Okay, we have got a breast cancer classifier, so we have got a data set based on that, right? So the how's the breast cancer data set going to look like? Okay, if I try to make it here, I could show you as well, but there's no point. It's a pretty simple example. So I'll get something like features. Okay, the cancer features, so they can be like radius, like the radius of the tumor that we are talking about, right? Then maybe we can have area, right? Of course we can have. We can also have the perimeter, right? We can have all these features regarding the specific, tumor that we are talking about. And the last one will be the target feature, meaning, we can write it as target here, which basically will consist of 0 or 1, because it is to decide whether the cancer is benign or malignant. Okay, so this is how a typical, data set looks like. Especially in this case, this is how it will look like. Okay, so if I make it, this tabular form data set will be, the typical data sets that we deal with. This is how they look like. They are in the CSV format. Okay, now coming back to the original question, what is a dimension? So a dimension, you can understand that it is nothing but an axis in the geometric space used to represent a feature. Okay, no need to memorize the definition, but I just wanted to state the formal definition. So what are these right here? Okay, let me change the color. Okay, so what is this right here? This radius, it's a feature. A feature for what? the cancer or the tumor that we're talking about, right? What is this area? It's another feature to represent the specific cancer. Then the perimeter is also a feature. There can be another feature called as texture. There can be another called as width, another called as thickness. There can be many of them. Okay. So what are all of them? They're features which are, trying to represent the cancer in a way or the other. So the thing with these features is, let me try and show this to you. So how do you think radius is going to look like? Okay, radius, if we are talking about maybe like a sphere, okay, just hear me out. Maybe like a sphere, radius can be like any value from 0 to, well, it can be any number, any large number, maybe infinity. It can be any number, right? So it will look like this, okay? What about area? How will area look like? So if we are talking about a sphere specifically, area can be, something like this. This is, I think, the formula. Okay. What about the perimeter? So there is no perimeter of a sphere, right? So maybe it's a blank column. We don't know. The point is that all these three features are going to look very different. They're going to increase very differently. When I plot them on the number line, when I try to see how they're increasing, how they're decreasing, it is going to look different. Which is why, whenever we try to build a model based on these features, we try to give them a separate axis of their own. What does axis mean there? Don't worry, it is the same axis that we talk about, when we talk about the coordinate system, like the x-axis and the y-axis. So let's say that to represent the radius, maybe I can say this is an axis which is representing radius. Okay. It can be pointing anywhere. I have just made it like this. Okay. Let's say that area can be something like this. Okay. Area can be something like this. What about perimeter? I don't know. Maybe it can be something like this. Maybe it can be pointing some other direction as well. Let's say we have got thickness or texture. So let's say texture can maybe point something in this direction. Okay. So this is how, these features are represented in the feature space or in the coordinate space, because this axis, all these axes that I've drawn right now, these are nothing but just the coordinate space, the xy plane or the xyz plane. It can be any plane that we want, where we are trying to represent the features. Okay. And these axes that we are drawing, these separate axes, they are called as nothing but dimensions. Okay, dimensions. So very intuitive, very simple to understand. Okay, this is very important to still, put in your mind as to what are dimensions. Like when we speak, whenever we discuss dimensions, the immediate word that should click in your mind should be like a feature. Like if I say dimension, it basically means we are talking about a feature. Why? Because any dimension, it is basically used to represent a feature in the space. Okay. In the coordinate space. Okay, simple. So if you want me to write it, maybe I can write it. So dimension can be like each axis in feature space. Okay, wherever the features are drawn, or wherever the features lie, every axis, every separate axis represents a dimension. Okay, just remember that, simple as that. Okay. Now comes the main question. What happens when these dimensions increase too much? Okay, because if you look at the problem that we are dealing with initially, if you look at the problem statement for today, it is dimensionality reduction. See right here, dimensionality reduction. So it's like we have to reduce the dimensionality, which means that at some point it is too much. So when does it become too much? What happens then? Let's discuss that. So like I said, I basically took three features here as an example: radius, area, and perimeter. But we can maybe have a texture feature, we can maybe have a thickness feature, a width feature, volume feature. We can have many features depending on how the data set looks like. It all depends on the data set that we have got on our hands. Okay. So the point is that these dimensions can increase very easily, right? So if we have got D features, okay, like above in the table, we have got three features, right? This fourth one won't count because this is the dependent variable or the target variable. Okay, these three are the features which will be used for training any model. Okay, don't think about training right now, but of course these three are the ones which are in general used for training a model. Okay. So we have got three up there, so it will be like a three-dimensional data. If we have got D features, it is called as a d-dimensional data. Okay, why? Because d different axes will be required to represent it in the feature space. Okay, so I'm just writing it to so that we have, you know, a record of everything. Everything is super clarified. Okay, simple. Now, now comes an issue. What happens when this d increases? Okay, because like I said that we can have any number of d depending upon how the data set looks like, what the data set is given to us. So it can scale up to 20, 25, even 30. Okay, what happens then? Is it bad? Is it good? Let's discuss that. Okay, so now comes the issue that what happens. So you know, when this d increases, very simple thing happens. One thing we can say is, as the first observation, the volume of feature space grows. Okay, what does this mean? So earlier, if we come back to the diagram, this diagram right here, do you see how this feature space is looking like? It is looking so naive, right? So simple. There are only four features. There's area, perimeter, radius, and text. Text is texture. Let's say that I make a thickness feature right here. Okay, simple. Let's say I make a volume feature right here. V. Let's say I make a width feature right here, W. Do you see how dense this feature space is starting to look now? Everything is becoming crowded. So we can basically say that the volume of our feature space is growing too much as the features are increasing. Okay, they are basically increasing too much and they're covering a lot of volume. Okay, simple as that. This is nothing big, it's just a simple observation that we are making. It will be useful for you know, whatever discussion we do in the future. Okay, now what happens when this dimensionality or these number of dimensions grow? Okay, what happens now? They basically lead to a lot of disadvantages. There are hardly any advantages of dimensions growing, and I'll tell you why that happens. So if we are talking about the disadvantages, you know, let's first talk about the primary one, which is distance loses meaning. Okay, distance loses meaning. Okay, what does this mean? So let me get back quickly to the diagram once more so that this can be clarified. So when you look at the diagram and you know, like we stated that as the volume is growing or as the dimensions are growing, the volume of the feature space is going to increase too much. Now you know, whenever we now in this data, in this high dimensional data, whenever we try to use like a distance based model, something like the most simplest, let's take KNN. Okay, it's a distance based model where we calculate the distances. So let's say that we are trying to use a KNN model in this case. You know what will happen? The distances that we calculate, where you know we use something like a Euclidean distance. Okay, let me quickly like write it. So you know we calculate distance like the Euclidean distance, right? I think this is the formula, right? If it's incorrect, you can maybe correct me, but you know, that's not the point right now. The point is that maybe this is the distance that looks like that we calculate in KNN. Now, the thing is, whenever the data becomes high dimensional, like the one that we have right now, this distance value starts to lose its meaning. Because since the data is so dense, the features basically lose the meaning of distance. Because you know, whenever we go and calculate this formula, for let's say any two features in the feature space, the far points and the near points, they become indistinguishable. Okay, meaning that you know, let's say that we have got this line right here. Okay, and I have got a point A here, then the center O and the point B. Okay, then I've got maybe a point P here. Okay, and I've got this O right here. Now you know, if I ask you a very simple question, how will we calculate the distance from P to B? This will be the distance from P to B. You can calculate it using any distance measure. So you know, distance from P to B will be like BO minus PO, right? Basically it is this distance minus this distance. and I will get this much, right? Simple. So the thing is, in this case, since the dimensions are only one on this line right here, the distance between points is very interpretable, right? It is distinguishable. I can easily say P is very close to B, right? And I can also say that P is very far from A, right? Because I can say that this BP is, let's say, like 2 centimeter, and this AP is maybe like 10 centimeter, and I can easily say that, the point P is very close to B, but it is very far from A, right? I can very easily make this conclusion. Why am I able to make this conclusion for this simple example? Because I can distinguish between the far points and the close points. Okay, so maybe P can be called as a close point. Why? Because it is close to B. Simple as that. See, it is so close to B. And A, maybe I can call it a far point. Why? Because A is too far away from P. Okay, you can even see it in the diagram, but even if you calculate it on the number line, we are getting like a higher result. Like for this, the distance is too much, for this, the distance is low. Hence, this is a close point and this is a far point. We can very naturally, arrive to this conclusion, to this result. But the thing is, when the feature space grows, like it did in our example, so let me quickly go back to the example. In this example that I do, when the feature space grows too much and I try to calculate the distance, okay, so now what happens is that the distance between any 2 points becomes less interpretable, because I now cannot distinguish smoothly between the close points, okay, the between the points which were lying close and the far points. So the close points and the far points become sort of indistinguishable when dimensions increase. Okay. So when dimensions increase, it becomes difficult to understand how distance based models are going to work. Okay. That's the thing. That's the number one disadvantage that we have of basically our dimensions increasing. Okay. Now, number two. Number two is also pretty simple. It is noise accumulation. Okay. So the thing is that whenever we talk about a data, any data set that we talk about, it has got relevant features and irrelevant features, right? Relevant features are the one which are, most closely related to basically predicting. For example, let's say I've got breast cancer classification problem here. So let's say I have to predict that whether the cancer is benign or malignant. Now, some of these features are going to be very useful in doing that, but some of them, they are not going to be as useful. Okay, those features classify as noise. They are called as noisy features because they are doing nothing in helping me training the model, but they are just contributing to the noise, right? So I don't actually need those features. Now the thing is, when we have a low dimensional data set, okay, something like let's say a two-dimensional data set. Let's say I only had radius and I only had area. Now in this case, since there are only two features, both of them will be considered very, very relevant, very, very useful in predicting whether the cancer is eventually benign or malignant. Okay. But if let's say I have got 30 features, 30 different dimensions. Okay. In this case, I have got two. I have got radius and I have got area. What if I have got 30? Now, if I have got 30, suddenly the chance of having noisy features has increased. Why? Because the number of features is too much. See, the thing is, not all features contribute equally to the model learning. So, if your features have scaled up too much, if your features have increased too much, the chances of having noisy features also increases a lot. Okay, so noise accumulation is a major challenge. Okay, basically, irrelevant features increase. If I want to write it, irrelevant features increase or accumulate, whatever you want to call it. Okay, the third one. Now since the third one is like a derivative of the second one, so if noise is increasing, what risk does it carry? Since we know whenever noise increases too much, the model, if it runs for a long enough time, for long enough epochs, or for long enough iterations, it will try and memorize the training data. What happens if the model memorizes the noise in the training data? Overfitting. Classical machine learning problem. Okay. So this noise accumulation also leads to overfitting risk. Okay. And this is all due to the single problem that we were discussing, which is nothing but dimensions increasing. Okay, so there is again an overfitting risk. Okay, what is the fourth one? It's very simple. It is difficulty to visualize. Okay, this is the simplest one to understand out of the four. So what is visualization? It is basically, understanding your ideas by looking at them or imagining them in the form of maybe like a picture. Okay, so I've got this disk right here, this solid state, right? Now I can touch it, I can feel it. Now what is this? What is this shape? It's 3D. Why? It has got three dimensions. It has got length, it has got width, and it has got height. So it's a 3D thing. Now, if I take a paper on the other hand, like this is a paper. What is this? This is 2D, right? I mean, this is still 3D because it has a micro something thickness, but maybe we can consider it 2D. What I write on the paper, it will be considered as 2D. Okay, now 2D and 3D is within our scope of visualizing, within our scope of seeing, touching and experiencing. But when the data scales up to 4 dimensions, 5 dimensions, 30 dimensions, we cannot visualize it, not in our minds and not on paper. See, if I could make it right here, how do we make the x and y axis? This is the x-axis. So whenever we are talking about one dimension, it will either be the x-axis or the y-axis. When we are talking about 2, it can be the y-axis. When I'm talking about 3, it can be the z-axis. Now, when I'm talking about a fourth, I can maybe go on and make something like an l-axis right here. Then a fifth, I can make an m-axis. But this is not a clear visualization, right? This is not intuitive at all. We don't know what planes this and this is lying in. So whenever the dimensionality of data increases, it becomes very difficult to visualize it, especially visualize it in a natural way that we usually do. So this difficulty to visualize is a major problem, because if we cannot visualize the data that we are working with, then we cannot be confident in building a machine learning model, because eventually all models depend on the data that we are building it upon. Okay, so this is also a major issue. So we have till now discussed four major issues that come to mind whenever we talk about dimensions increasing. Okay, what is the first one? The distance losing meaning. Okay, so they're all very intuitive to understand, very simple to understand, and they're very real world problems. All of them do happen in any real world high dimensional data set. Okay, and usually real world data is high dimensional because there are a lot of features which are used to predict the target variable. So what do we do about it? Okay, first of all, what are these problems collectively called? So all of this ruckus that increasing the dimensionality is causing, basically increased dimensions are carrying all of these problems. So these problems are collectively called as the curse of dimensionality. Okay, very popular statement in machine learning. You must have heard it, the curse of dimensionality. Okay, it is called as a curse because it does not bring along a single advantage but multiple disadvantages. Now I have stated only four. There are many more that you can go and read, but these four are the most important to what we are discussing today. I have put a link in the description for an article about curse of dimensionality, so you can read about it as well. But these four are the most important because basically we are going to implement the PCA model later, so they are very relevant to what we are discussing. Okay, and all of these disadvantages combined that come in our model upon increasing the dimensionality are called as the curse of dimensionality. Okay, simple till now. Now we saw that increasing dimensions is causing all of these problems. So what do we do? Simple. Let's decrease the dimensions. Let's reduce the dimensions, which eventually brings us to our problem statement today, that we wanted to reduce dimensionality. Okay, we wanted to reduce dimensionality. Okay, so now, very important, very important. uh, why are we doing this? See, one way that we can understand this, we can say it simply that we are trying to reduce the dimensionality because we have got these four or a multitude of disadvantages that we are trying to avoid, and avoiding them can basically bring us this cleaner version of a data set where we have a data which does not have all these problems. It is correct, okay. But what we can also say is that dimensionality reduction will help us having a data set which is carrying almost the same information as the original data and far less features. Okay, so what does this mean? Now let's say we have a huge dimensionality data set, like a 30 dimension data set, okay, which is carrying nothing but 100% of the information in the data. Okay, simple, since 30 dimensions means all the 30 features, so it is carrying 100% information in the data. But like I said, much of this information can be noise, okay, basically irrelevant features. So much of it is going to be noise and the rest is going to be the relevant data. Okay, basically the data that consists of patterns that we want our model to learn and eventually build a high accuracy model. Okay, so what do? We try and reduce this 30 dimensional data to something like a k dimensional data. K can be anything, we'll try to figure that out later, I'll explain it, but currently just look at it. We are trying to reduce it to something like a k dimensional data, and that k dimensional data will represent or contain about 95% of the original data patterns. Now where did the rest 5% go? That rest 5% is the noise that we were trying to avoid. Okay, so this is like a win-win situation. See, we are saying that 30 dimensions are used to represent the entire data. Let's not take 30. Why? Because it is bringing so many problems. Let's take some number less than 30, and that way we can represent the data as well, and at the same time we can sort of ignore the noise. We can sort of keep the noise away by reducing the dimensions. That is the intuition that we are trying to do here. Okay, and again, let me go back to our original assumption, our original understanding that we had. 30 dimensions here means nothing but 30 different features. So like 30 features are used to represent the breast cancer data set. We don't need 30. We need some number less than 30, and that will also give us highly accurate results without this noise and without all of these disadvantages that we just talked about. That is the intuition here. Okay, now very important, very important. What Why does dimensionality reduction work? Like we just discussed that it will get rid of all these disadvantages, but what are some other reasons that dimension, when we reduce the dimensions, it might work? Okay, so we can say the first reason, which is very intuitive, is that features are correlated correlated and carry same signal. Okay, what does this mean? What does this mean? Now this is very simple. I'll explain it to you using an example. Let me take this one right here. Okay, let's take this one. Okay, so if I go back to the board, so let's say that I have an area feature, an area for the sphere. Okay, let's say that the cancer was spherical in shape, and this is how the area looks like, right? Of course. Now what does the volume look like? The volume looks like this. Okay, and I've got another feature where I'm having the radius. Simple, right? Now answer me one question very carefully. Look at all three of them. It's very simple to understand this, and answer me this. Can I say that these two, area and volume, are correlated to each other? Okay, can I say that this volume right here and this area are correlated? The answer is yes. Very simple as that. Why? 4 pi and 4 pi are common in this. 3 is a number, which is, numbers can be ignored, and there's r square here, and there's r cube here. If we have the value of r, we can calculate both of them. We don't need to keep both of them. Okay, so this is like a very simple example. This is not what actually is happening, but I just wanted to explain that in this case these two features are correlated. Okay, and if I am having the answer for area, I can also very easily get the answer for volume. There is no point on keeping both of these features in the dataset at the same time. It will lead to unnecessary redundancy. Why? Because these features are correlated to each other. Okay, and they are carrying the same signal, meaning that when I train the model, both of them will give us approximately the same values. They will contribute almost equally to the model. No need to keep both of them. Okay, this is the primary reason as to why, whenever we do the dimensionality reduction process, it works. Because many of these features, this is just one example. I talked about a 30 dimensional data set. So maybe there are many other features which are correlated. They are contributing the same signal to the model. I don't want the same signal, I want different signals, because there is no point on getting the same signal again and again. That will lead to unnecessary redundancy, which we are trying to avoid. Okay, so this is the number one reason, that features are correlated and they might carry the same signal, so we don't need those, and we can reduce the dimensions that way. Now what's the other one? There are more. There are a total of three actually. So if we discuss the second one, it is similar to the one that we discussed above. Some features are dominated by noise. Very simple. So some features contain only, noisy data or noise, which we don't actually need inside the model. So we try to ignore them completely. Okay. That is the second reason why this dimensionality reduction process works very intuitively. Okay. What is the third one? Very important, very important. What is the third one? Features carry zero or near zero variance. Okay, variance. Very important. Why did we suddenly mention variance here? And what is the significance of variance here? So guys, this brings us to the second most, important checkpoint in the video about variance, because, this variance concept will be used too much in this video a little while later. So let's discuss it in depth. So, whenever we talk about variance in terms of machine learning models, especially in the terms of dimensionality reduction, so whenever we talk about variance, what we actually mean is signal or underlying pattern. Okay. What does this mean? So, as we discussed in the first point, let me quickly scroll back up just a second. So, as we discussed in this first point right here, features are correlated and they're all carrying some signal, and we don't want the same signal. We want different signals. So whenever we are talking about differing values, we are thinking in the terms of variance, because variance is, more intuitively related to probability, which is why we can map it to these math concepts. Okay. So variance in the data set means that there is a lot of variation. The data set, the different feature values of the data set are not related to each other. Okay, they're having completely different scales. They're increasing and decreasing in different ways, and that is considered as good. Why is that considered good? Because if the variance is high in the data set, it means that the signal or the underlying patterns in the data set are present. We want those underlying patterns because that is what is used to train the model. Okay, if the model is it has zero or near zero variance, and if some of the features are not carrying all that variance, we don't want them. Why? Because they're not carrying anything that we can use to train. See, whenever we talk about training a machine learning model, we talk in terms of features. We need good features. And what are good features? Features which carry some signal now, features which carry some information that can be leveraged in the model, that can be used in the model to train them. But if they're not carrying any signals or any underlying patterns, then they are basically useless. Okay, and that signal or that underlying pattern is basically represented by variance. Okay, the same variance that we talk about in probability. Okay, so whenever our features carry zero or non-zero variance, we sort of need to reduce it, which is the third reason why dimensionality reduction works. Okay, So let me quickly jog your memory back. So we have discussed what a dimension is, okay, and why dimensionality, when it increases or scales up, it basically leads to a multitude of disadvantages, and we discussed those disadvantages, okay. They are collectively called as the curse of dimensionality. Hence, we need to reduce dimensionality, okay. And then we basically discussed how we need to go from like a 30 dimension or some high dimensional data set value to a k dimensional data set, okay. And these three are the reasons as to why this dimensionality reduction process works very intuitively, okay. Simple till now, very simple, okay. Now what happens after we have reduced the dimensionality? Let's say that we had this 30 dimensional data set, and now we have successfully converted it to some lower dimensional data. K is some value far lower than 30, something like, can say K is like maybe 2 or 3, something like that. Maybe it can be something else as well. Okay, we have converted this. So now after this, what has actually happened? What are the advantages that we have gotten? So there will be multiple ones. First of all, in the original 30 dimensional data set, we were having a risk of overfitting. Now in this lower dimensional data, we will have reduced risk of overfitting. Okay, simple as that. Training will be very fast. Okay, because the number of features are now very less, so training will be very fast. Only the relevant features are kept. Okay, visualization will be better since we have only got 2 or 3 features now. They are comparatively very simpler to visualize. Okay, so visualization is better. Okay, distance based models will now make more sense because dimensionality in less and again close and far points will become distinguishable, and all of the disadvantages that we have, basically those will be sort of reversed, and we will get like a good data set that we can now use to build any model. Okay, again, one thing I'd like to clarify: dimensionality reduction is not a machine learning model. Okay, it is used to reduce a data set to transform a data set which can then be used in any machine learning problem. Okay, remember this is not a training model. We are not training anything here. We are just changing the feature representation because not all features are useful. Simple as that. And because all of the disadvantages it carries that we saw in the curse of dimensionality. Okay, now let me quickly open the data set for you, and not the data set, basically the EDA which I have done in the code, so that we can get an idea as to what is happening. So this is the repo. I have left the link of the repo in the description. You are very welcome to check it out. Okay, so like I said, since we are only talking about benign or malignant tumors, this is a binary classification problem. Okay, and the problem in itself is not that important. It's an easy problem. We have done this before, but the main thing is this experiment that we did to compare how the classifier performance is changing before and after we have done the dimensionality reduction. Okay, so you can read this is very basic stuff to read. Okay, let me quickly scroll down. This is the pipeline that we have implemented. I will be discussing the code in detail towards the end, but first let's move on. So this is something you can again read. Okay, dimensionality and what reduction and increasing it does. I have discussed it all. Then the curse of dimensionality. Okay, now coming to the EDA. So we have done the EDA. Let me show it to you in the code. So these are our two standard libraries that we implement: NumPy and Pandas, the goat of machine learning. Seaborn and Matplotlib for the visualization. Time, I'll tell you why we have imported time. This was for the inference latency that we have calculated later. Okay. All this, they're all relevant to the model. We will discuss them later. First, let's get on with the EDA. So the breast cancer dataset that I've used for today, I wanted to make it a very easy one because, like I said, the model itself is not a problem. So I've taken an inbuilt dataset. These inbuilt datasets, they're very clean. There's hardly any missing values or stuff, so they're easy to work with. Okay, this is the dataset, target and data. We have taken it as that. Okay, now going on to the EDA. So I have basically tried to go for a heat map or a heat plot. So heat plot, it basically shows the correlation between different features. So for those who don't know, correlation, let me quickly tell you what it is. So correlation is like a mathematical term, okay? Correlation, it has an entire mathematical formula. This is probability and statistics, college level probability and statistics. It's basic pretty much. So it has a value between -1 and 1. Okay. The more it is towards +1, it means the features are highly correlated. Okay. And if it's towards -1, it means the features are not correlated at all, or they are completely separate from each. Like, let me get it in full screen very quickly. Okay. So this is the correlation heat map. So you can see different values. Okay. So there's another thing that you can do. So in the code, let me quickly open the code once more. So in the code, in this line right here, if you write a naught is equal to true, a double n o t is equal to true, what it does is it writes the values inside these colored boxes, the values of correlation. Okay. For example, let's say that this mean radius and this mean texture is correlated. If it was correlated by whatever value, then we will have some value inside this white box here, or some value inside this red box. Okay. But since it was a lot of features, too many numbers here would be confusing, so I avoided writing it. You can try it out if you want to. Okay. Here the color coding is very simple to read. If it is close to red or a dark red, it means that the features are highly correlated. The lighter it is, it means that the features are not that highly correlated. So when you just look at this heat map, you can basically get an idea as to why this dataset is nearly perfect to understand the impact of dimensionality reduction, because there are so many dimensions. These are all the dimensions from mean radius all the way to worst fractal dimension. So there are a total of 30 dimensions in this. Okay. And we have plotted this matrix, this heat map, in order to get an idea how correlated they are. So there are a lot of complex patterns lying inside this heat map. Okay. So we can basically decide from this that this data set has some highly correlated features and some which are not, and we need to reduce it from these 30 dimensions to some lower value. So let's get on to that. Okay. So you can read the other part of the repo as well. So this heat map itself, see, it gives us the correlations about the space, so you can see it. You can read all of this as well. Okay, there's no point of discussing this, I have done this before. Now coming on to the PCA, the main thing. See, what we have discussed till now is that dimensionality, what it is, what dimensions are, why it is a problem, and why do we need to reduce it. Now comes the main part. How do we do it? How to implement it? So one of the simplest ways to implement dimensionality reduction is via nothing but PCA. It is one of the most popular machine learning concepts, PCA. Okay. The full form is Principal Component Analysis. I'll tell you what principal component means later, but it is very relevant. But right now it will be difficult to explain, so let's just move on forward. So the PCA, it works like an algorithm, and before just tracing the steps of the algorithm, I'll try to tell you about it in a more intuitive manner, because there is no point in just copying the algorithm and moving on. Okay. So first of all, very important. So what are we trying to do? What is the original question that we are trying to answer? Okay. So as we discussed, we are saying give us some direction in the data set, right? Give us some features in the data set that are capturing maximum variance. Can we say this? Can we say we like need the direction that is capturing, or like the features that are capturing maximum variance? Can we say this? We absolutely can. Why? Because as I explained to you guys, variance is nothing but the patterns, or the underlying important information in the data set that we actually want for model training. We are after variance. We want the direction that has got the maximum variance. We want the features that carry the maximum variance with us, while we can ignore the others. Okay. So we can say we are trying to find a direction of maximum variance. Okay, good enough. Now what is variance? Okay, finally it's time to discuss it. Now variance, if I write it in mathematical terms, let's say for some feature x, it is nothing but the square of standard deviation okay, in the data. Or if I write the mathematical formula for variance, it looks something like this: xi minus x mean whole squared. Okay, no need to memorize this again. This is just basic probability and statistics formula. Okay, now look at the value inside the bracket very carefully. What is xi? Xi is nothing but maybe any data point. It can be any point, any value, right? Xi is nothing but a data point. And what is x bar? Okay, what is this x bar right here? X bar is nothing but the mean, right? So what is variance basically measuring? Like when I say variance, what do I mean? I mean, how much is the data varying from? Okay, like if I say that, don't vary away from the seashore, like you'll get lost, or maybe your boat will get lost. Like, so I say don't vary away from. So you will ask me that whenever we are talking about variance, we mean to assign a reference point. Okay, if I'm saying don't vary here and there, okay, or if I'm saying that this value is varying far away, now you'll say far away from what? So for variance we need a reference point, right? Because we are saying that it is varying, which means it is far away from there. It can be less, it can be high, but we need a reference point, right? So that reference point is nothing but the mean. Okay, so in this formula what are we doing? Why are we subtracting this xi from x? The reason is because we have taken mean as a reference point. We are saying that the mean, which is the average, represents the center of the data. Okay, and this variance is finding nothing but how much each data point is away from the center. Okay, this xi is going to represent different data points in the data set. Okay, like x1, x2, okay, and all the way up to maybe x of n. Okay, so it is representing different data points, and x bar is representing the mean. Now my question is very simple. What I am asking when I'm calculating variance is that how much are these individual data points away from the center? Okay, that is what the variance means. That is what means when I talk about the variance and when I want to capture the variance. Okay, so now what happens next? Once I've got the variance, now what do I want? Since I've got the direction of the variance and how to capture variance, what about the next thing? Now I don't just want the variance. I want the direction of maximum variance. Okay. Now how can we calculate the direction of maximum variance? So let's talk about that. Okay. Okay. So whenever we are talking about variance, it can be thought of in two terms. Okay. So variance can be variance in features itself. That is the first kind of variance that we can have. And there is another kind of variance. Okay, this is too light. Just a second, wait. Yeah. Okay. And what is the second kind of variance? Variance in relationship between two features. Okay. What does this mean? Very simple. See, one way to understand is let's say that we have a data set where we have got height and weight values. Okay. So let's say we have got height and we have got weight. Okay. So height, it can be like in feet and inches. So maybe this can be like the different height values, right? These can be like the different values of height that we have got. Okay, let's say we won't calculate anything, but I'm just asking you to imagine. Okay, and these are the different weight values that we have got. Okay, different weight values. Now, what can be the type of variances that exist? See, one of the variance that we can say is existing in this height feature. Okay. So I can say what is the mean or what is the average of all these heights. It can be something like h bar, okay, whatever that value is. And then if I want to calculate the variance in height, I will have to do this hi minus h bar, and then apply the entire variance formula that we discussed right here, this formula right here. Okay, so that will be the variance in height. Similarly, when I talk about the weight, what will be the variance in weight? Each individual weight value minus the mean of all the weights, and then the standard variance formula that we have got here. Okay, but there is another kind of variance. See, this variance value that we just discussed, the variance in height and the variance in weight, this is nothing but this is the individual variances, right? This is the variance in the feature itself, this kind of variance, this first variance. But what about the second kind? See, when we look at height and weight, you know it also captures a pattern. See, if we can say something like if 5 feet people have the weight 65 kg, then there is some correlation between the height and the weight as well, right? Which means there is some variance in the relationship of these two. Okay, now this term where we try to calculate the variance in the relationship between two features, it is a mathematical term which is called as covariance. Okay, it basically means the variance between the relationship of two features, covariance. Okay, the formula is similar to variance. It looks something like this. Okay, this is 1 upon n minus 1. Okay, so this is what the formula for covariance looks like. Okay, it is basically representing the variance, but rather than for individual features, it is talking about the relationship between two features. Okay, now again jogging back your memory very quick, why are we doing this? Why are we doing this? Because the PCA wants us to capture the direction of maximum variance. What is the direction of maximum variance? It can be any direction. Basically, it is the direction where the data is varying or going away from the mean or the center. Okay, and since we need to find its direction, we need to know what is the variance in the data actually. So it can be of two types. This is type 1, where there is variance with the features itself, and then there is variance with the relationships that any two features have with each other. Okay, and we need to capture both of them. So we have got variance with itself, which can be like this. Okay, this is variance of x with itself, which is nothing but what we are calculating. This is variance of y with itself, and this is how we represent the variance between x and y. This is basically how we write covariance. Okay, now we need something that can capture all of them together. Okay, because we need to represent this data mathematically. For that, we use something called as a covariance matrix. Okay, a covariance matrix. So the thing is that whenever you will see any tutorial for the PCA algorithm, they'll just trace the steps of the algorithm. It will be like normalize the data or take the data to the center, and then use the covariance matrix and so on. But you need to understand why we came to all this. So the reason we try to use a covariance matrix in this case, the primary reason is that we need some matrix, we need some structure that can carry both types of variances, the type that the feature has with itself and the type that the feature has with the relationship of the other feature, that is carried by the covariance matrix. Okay, it can be represented by this symbol sigma. Okay, looks like this. Especially for two features, it is very simple. Okay, so the diagonal values represent nothing but the variance that we were talking about, and the non-diagonal elements represent the covariance. Okay, so this and this are the diagonal values. They represent nothing but the variance. See, it is same like this, and these represent the covariance, which means basically the variance in relationship between the two features, this formula right here. Okay, So you see how this matrix basically captures all of these values together, which is why it is the most intuitive thing to use in the PCA algorithm. Okay. So now, what do we do in the PCA algorithm? Let's discuss it. Okay, that is step. So when we talk about the PCA algorithm, what are the steps that we do? So the first step, very intuitive, is to normalize the data. Okay, normalize the data, or you can say centralize the data. How do we do that? We calculate x prime as x of I minus x bar. Okay, the reason for this, very simple. We have already discussed the reason for this. The reason for this is that whenever we talk about variance, we mean how much the individual data point is varying from the center. So variance is actually not calculated from the edges or from the extreme corners. It is calculated from it is calculated with respect to the center. The reference point that variance chooses to calculate is the center. So we need to centralize our data. That is exactly what we are doing using this formula. So for entire all of the data points, we do this and we transform our data. Okay, so these values are also called as the raw values. Okay, the raw values. This x bar is nothing but the mean, and this x prime, it is nothing but the, you can say, like the transformed values or the centralized values. Okay, what is the second step? What is the second step? We build the covariance matrix. Okay, covariance matrix. Now why are we building the covariance matrix? We just discussed it right now. Why are we using it? Because we need some sort of a structure that can capture both of these variances together. One, the variance of the feature itself, how the feature is varying around the center, and the second, the variance in relationship between two features. Okay, and we discussed this using this height and weight example as well. Okay, so we need some structure to represent both of them, and they can be done simply by this covariance matrix. Okay, this can also be, written like this. Okay, this is another way to write the covariance matrix in, like, simple transpose form. You can write it this way as well. Simple. Okay, so the second step, we build the covariance matrix. Okay, it's the same one like this. Okay, this is built using these values of x right here. Okay, simple. These are the primary two steps. After doing these two steps comes the main thing. Okay, the main problem. So discussing PCA, what are we trying to do? Let's go back to the problem again. We want the direction of maximum variance, right? We want the direction of maximum variance. So let's assume it. Simple as that. Let w be a vector which is representing the direction of maximum variance. Okay, it can be anything, like I'm saying in the xy plane or on the coordinate space, let this be a vector w, and it is representing the direction of maximum variance. I don't know where it is pointing. I have right now made it like this on the screen. It might be pointing somewhere else. I don't know. I'm just assuming that, this is my direction of maximum variance. Okay, simple as that. Now, a very logical result is that if I have a data point x of I, multiplying it with the direction w, or projecting it with the direction w, this term right here, xi multiplied by w, will give me the maximum variance, right? Of course it will, because see, I am saying w is the direction of maximum variance, and I am saying xi represents the each individual data point that we have in the data set. Multiplying them together or projecting xi on w will give me the eventual maximum variance. This is basic linear algebra, right? It will give me that result. Okay. So now I basically have the maximum variance. So I can maybe take it as zi to represent it, and it looks nothing like this xi into w transpose. Why have I done the transpose? It is just for calculation's sake. Okay, if you don't do the transpose, the multiplication will not make sense. Okay, now again, what is this representing? W is nothing but the vector which is representing the direction of maximum variance. Xi is each individual point. Okay, and all I'm saying is that if we multiply them together, we will get the maximum variance, which is z of I. Okay, now very simple. This is for each individual point, right? This is still z of I. This is not a total result. This is for each individual point. So how do I sort of, collectivize it? How do I sort of try and, uh, get it for all the values? Nothing. Take the summation. So maybe I can write variance of z, okay, is equals to nothing but 1 upon n summation of I from 1 to n, okay, z of I whole squared. Okay, this is how I can write. Okay, this is how I can say that, I calculated the maximum variance. This is how I can write it for all of the I values. Okay, now I can change the zi, and I can write wt of xi inside it. Okay, and I can square it up like this. Okay, now we can basically open this result up. So we have got wt into xi. So if I try to open it up, I can write it like this: wt into xi multiplied by wt into xi, right? This is how I can write the squaring of results. Now, applying basic linear algebra on this, if I take the transform of this right here, okay, the transpose of this, I can write it as wt x of I multiplied by xi t of w. Okay, simple as that. Simple. Okay, and when I eventually try to open this up, I can now write wt. I can take xi and xit together in the bracket, and I can keep w as separate. Okay, this is what I can get. Okay, I'll tell you why this makes sense in just a second, but just look at this result. Okay, so look at how we have basically calculated it step by step. We assume that w is the direction of maximum variance. Okay, we can assume it, no one's stopping us. We multiply it by xi because xi is the individual data point, and projecting xi in that direction, in the direction of maximum variance, will actually give us the maximum variance. And when we want that total value, we can basically do this summation to get this finally. Okay, now we had this inside a summation block, this entire thing. So I can write it like this. Just a second. So I can write it like n summation I is equal to 1, and inside this entire bracket. Okay, and outside I still have a 1 upon n. Okay, now look at this very carefully. This right here, what is this? Look at this very carefully. Okay, what is this value right here? So we calculated a covariance matrix just a few steps back. If you go and look at it, this was the covariance matrix that we calculated, which is used to represent the data, basically used to represent the variance. Okay, now look at this result right here. Is it looking familiar? Yes, it is. It is what we have just implemented right now. Okay, so this is called, basically, this is mathematical simplification. You can skip it if you want to. I'm just trying to solve everything for you step by step. Okay, so we can basically replace this covariance matrix value right there. Okay, so I've got this 1 upon n summation I is equals to 1 to n. Then inside it I've got x of I multiplied by x of I transpose. Okay, got this bracket right here. Okay, and I've got another bracket right here. Here I can write w, right? Here we can write this sigma, which is nothing but the symbol for the covariance matrix that we declared above. So we can get this final result. Okay, we can say that the collective variance, okay, is nothing but wt multiplied by the covariance matrix multiplied by W. Okay, and again I need you to remember the symbols, because that is what is the main thing here. What is this W? It is nothing but our assumed direction. Okay, it is not a given direction, we assumed it. What direction? It is the direction representing maximum variance. Okay, we multiplied it with our data point x of I, and we said that of course multiplying it or projecting it on W will give us the maximum variance value. Okay, this is how we get the collective variance. Okay, and now no, the problem is still not complete. It's a bit of a big problem. Now we have got the total variance. Now what was our original question? We had to maximize the variance, right? We wanted to maximize the variance, right? So we want to maximize this variance value right here. Okay, so let's go ahead and do it. Now it's a problem to maximize this variance. So first we will do it, then I'll show you. So let's say that I try to maximize this value, and I get the value, and I try to calculate it. And so let's say I calculated it and I get the value of variance, and I get that maybe when we put W is equal to 2W, what will happen? Okay, put the value of W is equal to 2W in this formula and see what happens. What will happen? Nothing. It will be WT sigma W, and this 2 will be coming here. Okay, so has the variance increased? Okay, how? Okay, by taking W is equal to 2W, has this variance value increased? Yes, it has. It has become the double of what it was before. Okay, okay, so why not let's take it 4W. Okay, okay, what will happen then? When we take it 4W and we input it into the formula, we get something like this. Okay, now, is this value greater than the original one? Yes, it is greater than the original one. It is even greater than the value that we just got right now. Okay. Now, what is the point of this? Do you understand what's happening here? What's happening here is that variance is increasing arbitrarily. It does not have a pattern of increment. Okay. It's like I'm saying to you that, you have got a number n is equals to 1. Okay, and what I'm saying to you is that increase this number as much as you can. Now does this make any sense? Whenever I say to you increase 1 as much as you can, you will ask now, you'll ask a question, till where? Till when do you want me to increase 1? Why would you ask that? Because counting is till infinite. Okay, if you try and increase 1, it can become 5, it can become 100. Okay, it can go to ask you to increase the value of 1, it can increase to 5, it can increase to 100, it can go all the way up to infinity. And infinity is not a number, by the way. Infinity is just used as a representation for a very high number. So my point is that when I say that increase the value of 1, you will ask me, you will ask anyone, that till where should I increase it? Because increasing it arbitrarily, increasing it without a limit or without a constraint does not make any sense. Okay, so that is what brings us that when we are tasked with increasing this value of variance, we need to have a constraint to do it. Okay, so this variance that we just calculated, we need a constraint to maximize it, because when we just keep increasing it, it has no limit of increasing, it will keep increasing and it will not make any sense. So we need a constraint. So maybe we can say that maximize this variance with respect to W is equals to 1. Okay, so this mod of W that I have written, it basically means the norm of W or the value of the W vector. Okay, why do we take it as 1? Why not 5, 7, 10 or any other value? The point is that we can take it as some other numerical value as well, but basically taking it as 1 makes it a ground for much easier calculation, and it becomes like a much more simpler process to do. If you take it as some other number, the calculation will become way too complicated. Okay, so now we finally have the optimization problem that we wanted to do on our hands, and we have got this problem right here. Okay, so we have to maximize the variance with respect to this constraint that we have got on our hands. Okay, that is what we aim to do. Now how do we do it? Okay, so the thing is, so this is what our optimization problem has come down to. Okay, so we have to optimize or maximize this variance value with respect to this constraint right here. Okay, so now these types of optimizations, they are pretty typical now because we have done them before. So to do these types of optimizations, we use the mathematical operation of Lagrange multipliers. Okay, I have left an article in the description regarding Lagrange multipliers. You can read it as well. You can also skip this part because this basically dives too deep into the mathematics. By the way, this is not the first time that we are covering Lagrange multipliers. We have done it in the SVM video as well. Okay, so the Lagrange multipliers, the thing is that they are the perfect tool when we want to optimize a function with respect to some constraint. So let's say this is what the basically the steps look like. So you can write your function like this. Basically we have got two functions, fx and gx, and we want to optimize or maximize fx with respect to gx, right? Which is what we are trying to do in this case. Okay, this is our fx value, this is our gx value, this is what we are trying to do, right? So when we want to do this, first of all we have to represent our function in this form. Okay, and then to maximize it, we have to basically take its partial derivative and equate it to 0. These are the steps of using the Lagrange multiplier. Step 1, step 2, respectively. Okay, so if you can, maybe we can skip this part and go over it quickly. So when I write down the equation of how it looks like, it will, we basically have to input the values in here. It basically looks like this. Okay, minus of lambda. This is what the eventual optimization problem looks like. We take the derivative of this. Okay, you can calculate it. It's a very simple derivative. Take the derivative and we basically equate it to 0. Okay, now when we equate this derivative to 0, we finally finally we get a result. Okay, this is it. Actually, this is the end of most of the calculation. Now there is no more calculation for this video, so you can have something to celebrate. So this is the final answer. Okay, a lot of work is still left because we need to decode this and interpret this. What does this mean? How is this? What is this? Okay, very simple to understand. Quickly look here. What is this sigma? Do you remember what is this sigma? It is nothing but the covariance matrix, right? We are representing it using the covariance matrix. Fine, right? We did use the covariance matrix. Okay, what is this W? Do you remember what is the W? The W is nothing but the direction of maximum variance, right? It is the direction of maximum variance which we assumed, which we actually wanted to find. Okay, now what is the solution that is coming out? This is what the solution is looking like. The solution has the direction in it. Okay, and it is saying that I also have another value called as lambda. Okay, this is lambda. I will explain about it, but what is the point of this? The point is that the direction of maximum variance is correct, which means that the W vector we assumed looking something like this, and we said that this is the direction of maximum variance, we assumed correct. But the scale of that value, okay, by this is the direction of the maximum variance, but what is the magnitude of maximum variance? Only that value has changed, and that value is nothing but this lambda that we have calculated. This is nothing but the magnitude of maximum variance. Okay, so we have the magnitude of maximum variance and we have got the direction representing by W. Okay, so we finally have our answer. Now few very important terminologies. Okay, this lambda right here, this, okay, so to show that lambda is basically the magnitude of maximum variance, there's a very simple thing that you can do. So we got the value of sigma w as lambda w, okay, like the solution of the equation that we were solving. Now take this value and input it back into the variance equation. Now what is the variance equation? So the value of variance is nothing but this right here, which we wanted to maximize as our original. So let's input the value of sigma w back into this equation. So how will we do that? We will basically write variance of z, okay, the collective variance that we were trying to calculate. It was this w sigma into w transpose. So in place of this we can write this, okay, simple. So what do we get? We get lambda w multiplied by w transpose. Now w multiplied by w transpose is 1, okay, basic linear algebra result. So this variance, the value of this variance z, it comes out to be nothing but lambda. Okay, so this basically proves the hypothesis that we discussed right now, that this lambda is nothing but the magnitude of variance. Okay, simple as that. Okay, so now what actually happened? What did we do in all of this? So see, simple as that. We had a high dimensional data set. Okay, it had all of these axes right here. Okay, all of these axes, all of these dimensions representing different feature values, right? This is radius, area, perimeter, width, thickness, texture, okay, this is maybe volume, and we had all of these different features. Now our main problem, we don't want all of these features. We want only some of these features because they lead to a multitude of disadvantages, and I want to reduce them. So I maybe reduce them to a lower dimensional data. To go to a lower dimensional data, I need to retain only the useful features. What are the useful features? The features which represent or which have the maximum variance. How do I find the features having the maximum variance? I did right now using this optimization that we did for the PCA itself. And what it is saying is it is correct. The direction W that we assumed is correct, and the variance along that direction is nothing but lambda. So the magnitude of variance along that direction is lambda, which means that these features, let's say they get reduced to something like two features. Let's say only radius and area are left. We can say that the magnitude of variance along this radius is nothing but lambda 1, and I can say that the magnitude of variance along this direction for the feature A is nothing but lambda 2. Okay, and lambda 1 and lambda 2 capture most of the variance in this entire model. There is no need for this, and this. These were like noise for the data set. Okay, and basically, when we calculate the numerical for PCA, we get multiple of these lambda values like we have right now, and what we do is a very simple step. We sort them in descending order. Okay, and we take the top two values or the top three values. Okay, these top values that we take are called as the principal components. Okay, principal components. Okay, and why are the top two values taken? Because these are the highest values of what? Highest values of the magnitude of variance, which is what we wanted from the beginning. We wanted the direction which had the maximum variance. We assumed that direction to be W, but then we were like, okay, we have the direction, what is the magnitude? We found the magnitude to be some value lambda, and wherever we get this value lambda, we sort them and we take the top two values. Why? Because they represent the maximum variance. Okay, largest lambda value is called as, like out of them, let's say lambda 1 is larger. Okay, so the largest lambda value is called as the first principal component. Okay, lambda 2 becomes the second principal component, and so on we can get them. Okay, usually 2 to 3 principal components are taken, not much, because if we take too many principal components, it sort of defeats the purpose of having to reduce the dimensionality of the data set. Okay, so this is it. Okay, very important thing, one more thing, the w vector, which basically represents the direction of the maximum variance, is called as the eigenvector. Okay, I have, like I said, I'll repeat again, I have got an article which I have linked in the description regarding eigenvectors and eigenvalues. They are basically very fundamental concepts of linear algebra, and they are very related to this PCA that we just studied. If you are hearing about them for the first time, don't worry, they're very easy to understand, but just remember this for right now, that the significance of eigenvector and eigenvalue are very important in the PCA, because what's happening is the eigenvector is representing the direction of maximum variance. Okay, and now when we have the direction, we need the magnitude as well, and the eigenvalue is representing the magnitude. So if you have these two values, you have all that you need to find the direction and the magnitude for maximum variance. Okay, so this is what's happening in this case. This was it for the PCA model. I have okay. So what I have done is that I have left another article that you can definitely try out, and that article basically covers like a solved example of PCA end to end. So right now I'm not solving it. This video is already pretty long. That article will basically tell you about all the steps of the PCA that we just did. So the first step, like where we do this normalization of the data, then making the covariance matrix, and then going all the way to the end. Okay, where we are basically picking out the top eigenvalues that we want. Okay, and then selecting them as the top two principal components to represent our data. Okay, so this PCA, it's very important to understand, it is like a feature transformation. We are not doing anything special, we are basically transforming the coordinate space for our features, and we are reducing it because it is better. Okay, now let's get back to the repo, see what else do we have left. So this is the same mathematical derivation, you can read it from here as well. Every concept has been covered, the repo is super detailed. Okay, this is about the significance of eigenvectors and eigenvalues. Okay, uh, this is for the projection, simple. Now, very important, look at this amazing diagram. Let me copy this so that I can basically show it to you as to what do we mean by this. Okay, let me copy it right here. Aha, it's not, it's very small, just a second. Yeah, now it's fine. Okay, so now let's discuss this diagram. It's very easy to understand, but let's just try to understand it in a very good manner. So what is happening in this diagram? Now the thing is, we have got these components right here, which is nothing but the features that we were dealing with. Okay, we change the color quickly. Okay, so we have got this right here. Okay, what is this? It is 30, which means that, just a second, the thickness is not right. Yeah, it's fine now. So this means that 30 so we have got 30 features right here. Okay, and what's happening is that this is the cumulative variance, which means the explained variance. So 30 features explain one of the variance, which means the whole variance. So if I want to write it, maybe I can say that you know 30 features, which is the total features in the data set. So I can write like 30 dimensions are representing 100% of the data, right? Or one whole part of the data. 100% just means 100 divided by 100, which means one whole part of the data, which is what is there on the y-axis. See, on the y-axis we have this one right here. Okay, so 30 features are representing nothing but the entire data, but like I said, it is unnecessary, right? Because much of it is basically noise, so we settle for far less number of components. So as we see in the graph, You see, at 25 it is also near about 100. At 20 and 15 it is also again near about, this is near about 100 itself, right? But when we go on to 10, what do we see? When we take only 10 features, the value has sort of come in the middle. So if I make a dotted line, it's like it is between 9 and this one value here. So it can basically be like 0.95, right? Which is nothing but 95% variance. So this is basically the variance ratio between the explained variance and the cumulative variance, which is, it's basically telling us how much variance did we actually need, how much variance the dimension reduced model is actually capturing. Okay, so you can read this as well. Now, the time and space complexity. So, we are doing a covariance matrix calculation, which we did. So we are calculating basically for all of the original features, and the covariance matrix is a 2D matrix, so it will eventually scale up to d square, and we have got n different samples. So the time complexity to calculate the covariance matrix is nothing but n d square. Okay, and this is the complexity for the eigen decomposition for the entire D into D matrix. Okay, this might increase too much in some specific problems, but usually it is fine. Okay, so, and then we did the projection, where we multiplied the each of the individual data point x of I with the direction vector w. So when we do this, we get another ndk time complexity. Okay, n for the number of samples, and d into k was basically the size of the projection matrix. Okay, so this is the total value of complexity, all of these three values combined: ndk, d cube, and nd square. Okay, as for the space, we only need to take into account as to what the model is storing. Okay, so the PCA model, it does not store much. It only stores the covariance matrix, which had a d square size for like a single component, and the projection matrix. Okay, so this you can say is the space complexity. Okay, now these are some geometric assumptions about PCA. Can read them. It is nothing new that we have discussed. It assumes Gaussian like data, which means the bell shaped curve, because variance is a complete summary for the Gaussian distribution. For different kinds of data, maximizing variance based directions, basically doing what we have done today, won't be the best choice. Okay, this is the model performance comparison. Basically, we applied the logistic regression model to build the breast cancer classification model. So this is the accuracy precision values before the PCA, and this is after the PCA. So of course we can see the accuracy has increased a little bit, and so has the precision. All of the metrics have slight changes in them. So this basically proves that PCA is working very well here, because we have got only 10 components, 10 dimensions, which are capturing 95% of the variance. So our task has been accomplished successfully. Okay, this was the interpretation. You can read this. This was the visualization. We can still not really visualize 10 components. We reduced from 30 all the way to 10, but we still cannot visualize 10 components, right? So we even scale it down to 2 so that we can get some sort of a visualization. Okay, this is the visualization. You can see this is how the separability looks like. Okay, failure case analysis, very important. These are some of the cases where the PCA model will fail. So the first one, as we read before, if the data is not represented by Gaussian distributions, if it is like a heavy tail data or a separate data altogether, then applying PCA won't be the best thing to do. Okay, scaling in sensitivity is all, of course, there. We normalized all of the features before before moving forward with the PCA algorithm. So if we have got very large numerical values, then some of those values will try and dominate the data set. We don't want that, which is why we bring all of the features to a comparable scale. So PCA is scale sensitive, and we need to take care of that. Okay. Sometimes what happens is that like I said, we are trying to get something at about 95% of variance. Now sometimes the threshold for that is set too low. Let's say someone sets a value of 80%, they're comfortable with that. They're saying get me a model with 80% of variance, which captures 80% of the underlying patterns, and find me how many dimensions will do that for me. Now that threshold is very low. 80% is okay, but components will not be a very components will not be suitable in this case. Okay, so this is basically the case of very aggressive dimensionality reduction, and this is not suitable. So setting the threshold value is also crucial in this case. Okay, you can read the others as well. These are some of the takeaways, and now we come to the code part. So if you want to check out the code, it is not all that complicated. It is basic implementations. Okay, so this I have already discussed, basic libraries. One hot encoder is not being used here. I've just written it down. Okay. Standard scalar will be used here. Logistic regression for our model. And this is the syntax to import PCA. This is nothing to learn from. You'll basically have to memorize this or just get hands-on with it with your own practice. Okay. Dataset. This is how the EDA has been done. There's the scaling. This is important. We discussed if we don't do the scaling, it won't work properly because PCA is very much scale sensitive. Uh, 80-20 train test split classic. This is the test size 20%. Random state is equals to 42. Typical now. It is basically used for getting reproducible results. This is something additional that I've started doing basically to measure the training time and the inference latency. So this is how you can measure the training time. Take a start and then take an end and subtract both of them. Okay, this is the training time. See, now the training time will be this time, which is right now, minus the original start time. Okay, this is how you train a logistic regression model. I've given out the max iterations as 5000. You can choose some other value as well. Okay, the main point, this is how we visualize the PCA. Okay, now this is how we set the threshold value. Okay, this was the threshold value that we discussed right now in the in the failure case analysis. If this value is set too low, the results of the model will not be very interpretable and not suitable at all. So it will be like a very aggressive dimensionality reduction. We don't want that. So usually set a higher value for this. We set a 95% value, which is why we got very suitable results. Okay. Then we applied the logistic regression model again, this time after the PCA. Okay, and we did basically the same steps. This will give us a comparison table based on all of these metrics. Okay, and yeah, you can look at the results here again. This is what the table came out as. I basically made it in the repo again so that it looks more readable. This is all of the math that we have already discussed. Okay, so let me quickly show you. Yeah, see this. This is the inference latency. After PCA, it just takes a bit more time. This is like microseconds. Okay, training time is near about the same in both the cases, and rest of all the features are better after the PCA, of course. Not all that much, but there is still some improvement, so we will take it. Okay, this is it, I think. Okay. So guys, I think this is it for the PCA. Long video, very long model to be discussed. Okay. One very important thing, if you did not understand any part of the video, I definitely will recommend you to just quickly watch it again. Okay, I've tried to explain everything the best way I could. If you didn't understand, I have linked many articles in the description itself. You are very welcome to check those out. And if you still have a problem, one thing that I personally like to do very much, and I will definitely suggest to you as well, take a piece of paper, take a pen, write out all the calculations. Whichever part you find yourself stuck at, whichever part you think is confusing, write it down and revise it. You will definitely understand it. Okay. So with that, we come to an end for day 12 of dimensionality reduction using PCA, and I will see you tomorrow on day 13. Let's check out what do we have. So on day 13, we have MNIST feature compression using autoencoder. So this is close, very close to the PCA model that we have built. But yeah, more on that later. So thank you very much, and I will see you on day